Vectors in Geometry lecture series. We're very happy to have Jacob Lurie from MIT. There will be 4 lectures, today's, then Thursday, next week, Tuesday and Thursday, all of them 12:30, all of them in this room. And the title of today's lecture is Topological Quantum Field Theory.
So, thank you very much. It's very nice to be here. So, before I begin, just let me say that everything I'm going to talk about grew out of joint work with Mike Hopkins and was inspired by the work of Kevin Costello. So I'm going to be talking about topological quantum field theories in these lectures, and I think I should start by reviewing Atiyah's definition of a topological quantum field theory. So first let me set up a few ground rules for these lectures. Whenever I say manifold, I'm going to mean a smooth, compact, and usually oriented manifold. And they will usually have boundary. If I mean to indicate a manifold that doesn't have boundary, I'll call it a closed manifold. So closed manifolds of a fixed dimension can be organized into a category. So let me introduce a category which I'm going to call Cob-D. So Cob-D is a category whose objects are closed manifolds of dimension d minus 1. And the morphisms are given by Cobordisms. So if I give you 2 closed d minus 1 manifolds M and N, Homs from M to N is going to be the collection of Cobordisms from M to N, that is, N manifolds B, such that the boundary of B is identified with the union of M and N, say where N's orientation has been switched. And I'm going to consider 2 Cobordisms to be the same as a morphism in this category if they're diffeomorphic, or diffeomorphic relative to their boundary. And finally, composition in this category is given by gluing. So, for example, let's say d is equal to 2. Here's a typical picture of a morphism in this category. It's here M is 2 circles, N is 1 circle, and here's a picture of a Cobordism from 2 circles to 1 circle. And if I say wanted to glue that, compose that with this morphism, then I would just glue these 2 pictures together along the common part of their boundary to get another Cobordism now from 2 circles to 2 circles. So with this terminology, I can give you Atiyah's definition of a topological quantum field theory. A topological quantum field theory, or TQFT, of dimension d is a tensor functor Z from this category I just defined, Cob-D, into the category of complex vector spaces. So here, when I say tensor functor, I mean a functor that preserves tensor products. So the tensor product on the right-hand side is the usual tensor product of vector spaces. The tensor product on the left-hand side is given by disjoint unions of manifolds. So more concretely, tensor functor means that if I take a disjoint union of 2 manifolds M and N, then and apply Z, the result is supposed to be the tensor product of Z of M and Z of N. And not only should I preserve, say, 2-fold tensor products, I should also preserve 0-fold tensor products. I should preserve the units with respect to the tensor products. So for example, Z of the empty manifold is supposed to be identified with the unit with respect to the tensor product on complex vector spaces, which is just the complex numbers. All right, so just to get us all on the same page, I'd like to spell this out in more detail in the case d is equal to 2. So what does it mean to give a two-dimensional topological quantum field theory? Well, first of all, I have a tensor functor which I can evaluate on the objects of Cob d. d is equal to 2, so the objects are manifolds of dimension 1, closed manifolds of dimension 1. And there's one particularly interesting manifold of dimension 1, namely the circle. So if z is a two-dimensional TQFT, I can evaluate z on the circle, and I get some vector space, which I'll call A. So A is a complex vector space. And once I know A, I actually know what z does on all objects, because every closed one manifold is just a disjoint union of finitely many circles. And remember, z is required to be a tensor functor. It's required to take disjoint unions to tensor products. So for example, if I wanted to evaluate z on 3 circles, then I would just get the tensor product of 3 copies of A. Of course, we're not done. Z is a functor, so we don't just have to say what it does on objects, we also have to say what it does on morphisms. So here's a particularly interesting morphism that I've drawn for you already, called a pair of pants. So if I evaluate z on that pair of pants, the pair of pants I've drawn, it's a bordism from 2 circles to 1 circle. So this is supposed to give me a linear map from A tensor A into A. So let me call that linear map M for multiplication. So if we play around with the axioms, you can learn the following things. Note that M is associative and commutative. So for example, M is commutative because there's a diffeomorphism of the pair of pants which swaps the 2 incoming circles, which swaps the 2 legs. There's also a unit with respect to this multiplication. And to get at the unit, you can evaluate C on a disk. So consider a disk, which I'm going to draw in the following way. Think of this disk as a bordism from the empty set to 1 circle. Well, that's supposed to give me a linear map from z of the empty set, which I said over there was the complex numbers, into z of a circle, which is A. And such a linear map I can just think of as giving me an element of A, i.e. z of this disk gives me some element which I'll call 1 inside of A. And again, if you play around with the axioms a little bit, you'll learn that that element 1 is a unit with respect to this multiplication. But of course, this is not the only way that you can interpret the disk as a morphism in this category Cob2. You could also read the disk in the other way. Think of the disk as a bordism from 1 circle to the empty set. And if you do that, well, z of the disk is going to be a linear map from A into the complex numbers. So let me call that linear map TR for trace. And again, if you play around a little bit, you note that the trace pairing is non-degenerate. So what's the trace pairing? Well, I mean, it's a bilinear form on A, which is given by taking 2 elements of A, first multiplying them, and then taking the trace. Or in other words, this linear map from A tensor A to the complex numbers is also what you get if you evaluate Z on this bordism from 2 circles to the empty set given by a cylinder. So you have this trace pairing, and if you play around with the axioms, you learn that this is actually a non-degenerate pairing. It identifies A with its own dual. And in particular, A is finite dimensional. So far in this discussion, we started with a 2-dimensional topological quantum field theory, and we extracted some algebraic structure from it, namely a vector space with a commutative and associative multiplication and a non-degenerate trace. Now that algebraic structure has a name. It's what people usually call a commutative Frobenius algebra. So, in summary, A is a commutative Frobenius algebra. That just means that you have all of the structure which I just described. Now, there's a Folk theorem, which is a sort of converse to this observation. Namely, if you start with a commutative Frobenius algebra, well, then you can reconstruct from it a topological quantum field theory of dimension 2, which is unique up to isomorphism. That topological quantum field theory will have its value on the circle be the commutative Frobenius algebra that you started with. The multiplication that you get from a pair of pants will coincide with the multiplication on your algebra, and the trace that you get from a disk will correspond to the trace on your algebra. So, i.e., TQFTs of dimension 2 are the same thing as commutative Frobenius algebras. All right, so now let's return to the general case where dimension D is large. So when D is equal to 2, we sort of analyze the notion of a topological quantum field theory by emphasizing what it does on manifolds of dimension D minus 1. If you evaluate Z on a D minus 1 manifold, you got a vector space, and then those vector spaces have some structure that you get by evaluating Z on Cobordisms. And when D is equal to 2, it's fairly comprehensible what that structure is. We see the structure of a commutative Frobenius algebra. But there's another point of view that you could take. Let's just imagine D arbitrary now. And now suppose that M is a closed D manifold. Well, a closed D manifold can be thought of as a Cobordism. It's a Cobordism from the empty manifold to itself. So Z of M you can think of as a linear map from Z of the empty manifold to Z of the empty manifold, which, remember, Z of the empty set is just the complex numbers. So Z of M gives you a linear map from C to C, and that linear map is just multiplication by some scalar. Lambda, and I'll abuse notation by just identifying Z of M with that scalar. So what this is saying is anytime you have a d-dimensional topological quantum field theory, first and foremost what you get is an invariant that's associated to any closed D manifold, a number. And one point of view is that maybe that's the primary information that you're after. Or that's maybe the most interesting thing, these diffeomorphism invariants of manifolds. So then what does it mean that those diffeomorphism invariants come from a topological quantum field theory? What does that buy you? Well, what it buys you is a set of tools for computing these invariants. So for example, if you believe this Folk theorem, then if you start with a commutative Frobenius algebra, you should be able to construct a topological quantum field theory of dimension 2. And then you could evaluate that topological quantum field theory on a closed surface sigma. And you would get a number. And that number you should somehow be able to extract from that commutative Frobenius algebra. If you wanted to extract it, what would you do? Well, let's draw a picture of the surface sigma. Here's the surface sigma. You might now try cutting sigma up into pieces that are very simple. So here I've drawn a decomposition of sigma into pieces, each of which is either a disk or a pair of pants. And the behavior of our field theory on disks and pair of pants is precisely what's encoded in this commutative Frobenius algebra. So what you would do if you wanted to compute this number would just be to write down what all of the vector spaces were associated to these cuts and all of the linear maps in terms of the Frobenius algebra structure, and compose them and see what number you got in the end.
Is there a choice of Frobenius algebra that gives you the genus or something like that?
Is there choice of, well, I don't know if you can arrange that you get the genus, but let me give you two exercises just to see if you, so exercises for those who want to make sure they're understanding what I'm saying. So if the genus of the surface is equal to 0, then what you get, the number that you get is the trace of the identity element. And if the genus is equal to 1, then the number that you get is equal to the dimension of the Frobenius algebra. And for g greater than 1, it's more complicated. Or at least I don't know a simple thing to say other than it's some big sum of structure constants.
What's the simplest Frobenius algebra that allows you to distinguish all of the degenerate?
I don't know, if you took like C cross C with a non-degenerate trace, that would probably, I won't say for sure.
You take the complex numbers and take a complex number that's not a root unit.
Oh yeah, trace is lambda, and then you pick up powers of the Euler characteristic. Right, okay, so what are we doing? Right, so you can think of having this topological quantum field theory as giving you a set of tools for computing these numerical invariants that are associated to manifolds of the top dimension. And when d is equal to 2, that set of rules is very robust, because two manifolds you can decompose into very simple pieces by cutting them along circles. But for manifolds of large dimension, that set of rules is maybe not very useful, because if you have a d manifold for d large, you can't necessarily simplify it very much by cutting it along closed submanifolds of codimension 1. What you would really like to be able to do is, say, compute these invariants by cutting your manifolds up into very small pieces, like, say, by triangulating them. But if you triangulate a manifold M, if you want to imagine that M is gotten by gluing together the simplices of the triangulation, then you need to contemplate gluing of a more general nature than just gluing along closed submanifolds. You need to think about gluing along submanifolds with corners. And in the definition that I gave you of a topological quantum field theory, there's no provision made for that kind of gluing. There's only the definition mentioned only this category Cobb D, and in the category Cobb D, gluing enters because it's given by composition, but that gluing is always along closed manifolds of dimension d minus 1. So you might regard this as a deficiency in that definition. That definition is sort of not encapsulating enough structure to really be able to compute these numbers. So for this reason, various people have proposed that there should be a more elaborate definition, which I'm going to sketch for you now. So definition sketch. An extended TQFT, again of dimension d, is a rule which associates some data. Let me to every closed D manifold, the data that you associate is a complex number. To every closed D minus 1 manifold, you associate data which is a complex vector space. To every Cobordism of D minus 1 manifolds, you associate a linear map between the corresponding vector spaces. And there's supposed to be some compatibility between what I said here on line 3 and what I said here on line 1. That is, if I have a closed D manifold, I can regard it as a Cobordism from the empty set to itself. And I'm supposed to get a linear map. That linear map is supposed to be multiplication by the corresponding complex number. Now, so far, what I've described is the sort of structure that you get out of a TIA's definition. This is the structure that you would have if you had an ordinary topological quantum field theory. To say that this is extended means you're also going to assign invariance to manifolds of lower dimension. So, for example, to a closed D minus 2 manifold, you want to assign some sort of information, and there's a lot of choices about what you could write here, but what people usually say is that you want to assign something like a C-linear category. That is, a category where the HOMs are don't just form sets, but form vector spaces over the complex numbers. So an example of a C-linear category is the category of complex vector spaces. And now to Cobordisms of D minus 2 manifolds, you want to assign some data, namely functors between the corresponding categories. And again, there's supposed to be some sort of compatibility between what happens on this line and what happened above. If I have a closed manifold of dimension D minus 1, I can regard it as a Cobordism from the empty D minus 2 manifold to itself. The functor that I get on the 5th line is supposed to be given by multiplication, or in other words, tensor product, by the corresponding complex vector space. So now I'm going to write dot, 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 meaning you're supposed to continue this all the way down and assign invariance to manifolds of all dimensions less than or equal to D. And the nature of those invariants, well, it becomes more and more abstract and as the dimension goes down. So dot, dot, dot is not meant to indicate that it's sort of obvious how you should continue this, especially what you want to write on the right-hand side is not very obvious. But it's not something that I want to say a lot about at this moment. So this is what an extended topological quantum field theory is supposed to be. And I should emphasize, this is really just a sketch. This is a very incomplete description of the kind of data that you want to have. That is, I've told you that you should have an invariant associated to every manifolds of every dimension less than D. But I haven't told you how these invariants should be related to one another. So in the non-extended case, they were related to one another by gluing formulas. That is, if you would understand, if you compose two Cobordisms, then the linear map that you got was supposed to be the composition of the linear map corresponding to the individual Cobordisms. So similarly here, there are supposed to be some sort of relationships between these invariants that will let you understand the invariant that's associated to a manifold made out of pieces in terms of the invariants associated to those pieces. Now in the non-extended case, we could sort of summarize those gluing rules very efficiently using the language of categories. As we could just say a topological quantum field theory is a tensor functor from one category, which is made out of manifolds, into another category, which is made out of vector spaces. And the philosophy is that you're supposed to be able to say the same thing here, but you have to leave the world of category theory a little bit and enter the world of higher category theory. So let me say a few words about that. So more precisely, an extended TQFT is a tensor functor not between ordinary categories, but between n categories, where on the left-hand side you have some sort of an n category made out of manifolds and Cobordisms between manifolds, Cobordisms between Cobordisms, and so forth. And on the right-hand side, you have some sort of linear algebra style n category made out of complex numbers, complex vector spaces, C-linear categories, and so forth. So I'm not going to say very much, especially in this lecture, about what an n category is, But
So is N related to D?
N is D. Thank you.
Well, whatever.
Yes. So I'm not going to say very much about what this is. I'll say more about it in the next lecture. So when you put this definition forth in this way, it might sound like the notion of an extended topological quantum field theory is a very complicated thing. After all, we now need to associate invariance not just to manifolds of dimension d and d minus 1, but to manifolds of all dimensions less than or equal to d. And we have to posit relationships between these invariants that involve gluing of very rather complicated sorts. But there's another point of view, which is that this notion of an extended topological quantum field theory is actually a much simpler notion than the notion of that I gave you originally of an ordinary topological quantum field theory. So this idea was articulated by John Baez and James Dolan in what they call the Cobordism hypothesis. So I just want to present right now a very informal paraphrase of the Cobordism hypothesis. So extended TQFTs are easy, say, to describe or to construct or to classify. So this is, of course, a very loose paraphrase. They conjectured something more precise than this, and I will give a more precise version of this statement in a little while. But first, I just want to explain the philosophy, why you might believe something like this is true. After all, an extended topological quantum field theory is a lot of data. We have to assign invariance to arbitrary d-dimensional manifolds with corners, and d-dimensional manifolds, if d is large, can look very, very complicated. But they can look globally very complicated, but by definition, a manifold always looks locally very simple. By definition, a manifold always looks like Euclidean space locally. And so saying that we have an extended TQFT is a tensor functor between d-dimensional categories, it's supposed to be encapsulating the idea that we have a complete set of rules which will tell us how to compute the invariant that we're associating to a complicated manifold in terms of the invariance that we associate to some constituent pieces. So since manifolds are sort of locally very simple, we have that complete set of rules to describe an extended TQFT, we really ought to only have to specify what it does on very simple elemental bits of manifold, like points or simplices or Euclidean space or something like that. And then everything else will just be taken care of for us by this magical theory of n categories. So that's sort of the philosophy behind this statement, why you might believe something like this to be true. So, let's see. So let me take some time now and discuss the Cobordism hypothesis in the one case where we can really understand it with what we know so far. And that's the case where there's no difference between extended topological quantum field theories and ordinary quantum field theories. That's the case d is equal to 1. So if you thought that I started out by doing a really easy case of TQFTs when I took d is equal to 2, we're now going to do something even easier. So let's do the example where d is equal to 1. So let's say z is a functor from this Cobordism category cob1 into the category of vector spaces. So what can we do with z? What information is contained in z? Well, the first thing we can do is evaluate z on objects. And what are objects? Well, objects are zero-dimensional manifolds. Well, there's a particularly interesting zero-dimensional manifold, namely a point. But there's actually two of them, because remember that our manifolds are oriented. So the point comes in two flavors. It comes with positive orientation, and it comes with negative orientation. So we can evaluate z on either of these things, and we get vector spaces, which I'll call x and y. But these vector spaces x and y are not unrelated to one another. We can evaluate z, for example, on this bordism here. This you can regard as a bordism from 2 points with 2 different orientations to the empty set. So this should give us a map from x tensor y into the complex numbers. And similarly, we can evaluate z on this picture, which gives us a map from the complex numbers into x tensor y. And now an observation is these maps exhibit x and y as duals of one another. And in particular, both are finite dimensional. So that means that x and y are not really 2 separate pieces of information. Once we know x, we know y. Y is just going to be the dual of x. So rather than even recording that we have this other object y, let's just record a property of x, which is that x is finite dimensional. So once we know what our field theory does on a point, we know what it's going to do on all objects of the category Cob1. Because remember, objects are just finite collections of points, the points them having orientation. So here's a typical object in Cob1. Say 2 points with positive orientation and 1 point with negative orientation. And we know what our field theory z is going to do. It's got to take this to x tensored with the dual of x. So just knowing this vector space x means we know what z has to do on all of the objects of Cob1. But again, knowing what a functor does on objects is not enough to determine the functor. We also need to know what the functor does on morphisms. Morphisms in this case are given by 1 manifolds, or bordisms between 0 manifolds. But again, it's a tensor functor. It carries disjoint unions to tensor products. So every 1 manifold can be written as a disjoint union of connected 1 manifolds. So we only need to think about what z is going to do on connected 1 manifolds, connected bordisms. And there aren't many examples of those. In fact, there are exactly 5. So what are the 5 possibilities for what a connected bordism can look like? Well, here's a connected bordism. It goes from a positively oriented point to a positively oriented point. And in fact, it's the identity map in the category Cob1. So this has to go to the identity map from x to itself. I can take the same 1 manifold and orient it differently. And if I do that, then I get the identity map from x dual to itself. I have 2 pictures, which I've already drawn. Namely, I can take this sort of half circle here. This is supposed to give me a map from x tensor x dual into the complex numbers, and that map is just what I'll call evaluation. It's the natural map that I have from x tensor its dual into the complex numbers. And similarly, I could evaluate z on this picture here, and this gives me a map from the complex numbers into x tensor x dual, and that's the natural map that I'll call co-evaluation. And now there's only one other connected 1 manifold that I can write down. That's a circle. And what does z do on a circle? Well, to figure that out, it's convenient to break a circle up into 2 parts. Z of a circle can be written as a composition of what z does on 2 halves of the circle. So what are these vector spaces? Well, z of the empty set, that's the complex numbers. And z of 2 points, well, one of these points has positive orientation, one of them negative orientation. That's x tensor x dual, or let me describe it as endomorphisms of x. And now what are these linear maps? Well, this one is the co-evaluation map. Or in terms of this identification, I can think about it as the inclusion of the unit object into endomorphisms of x. And this morphism here, that's the evaluation, which in these terms corresponds to the trace on endomorphisms of x. Thinking of this as a matrix algebra, it's just summing the diagonal entries. So then what is z of a circle? Well, it's what I get when I compose the unit with the trace. In other words, what I get when I take the trace of the identity matrix, and the trace of the identity matrix is just the dimension of x. So to summarize, just knowing this vector space x, we can sort of figure out what this field theory is going to have to do on everything else. And you can sort of convince yourself by eyeballing the situation that in fact there's essentially a unique way to build a field theory. I've described for you what this field theory has got to do on objects and on morphisms, and you can sort of play around and check that everything is suitably compatible, and you actually get a tensor functor. So I want to call your attention to one detail here, which is kind of interesting. I mean, one-dimensional field theories, there's not a lot to say, as you can see. It's just determined by a vector space, single vector space x. But in other words, what the field theory does on a single point. But you could also evaluate the field theory on other manifolds to get invariants. Like, you could evaluate the field theory on a circle, and what do you do when you what happens when you do that? Well, you get an invariant, which is essentially the only invariant that a complex vector space has. Complex vector space is determined up to isomorphism by its dimension, and if you turn that vector space into a field theory, well, the invariant that's associated to the only interesting one manifold is just the only invariant, namely the dimension of x. So this is the kind of picture, it's a baby version of the kind of picture that I want to develop in this series of lectures. Namely, the idea, a more precise version of this idea is that field theory should be determined essentially by what it does on a point. So that's what you want to see in higher dimensions, but there's two obstructions to realizing that. So let me explain that a little bit. So what you want to say is that in all dimensions, an extended TQFT Z is determined by Z of a point. And we're going to encounter two issues with this statement. So first of all, we encounter a sort of issue of an orientation issue. So remember, the philosophy of this statement is that, philosophy behind this is that if we want to know what our field theory is going to do on a complicated manifold of large dimension, we should be able to assemble that from local information. And locally, manifolds are very simple. They all look like Euclidean space. But they don't really look canonically like Euclidean space. If you have a manifold of dimension n, at every point that manifold, it looks like the tangent space at that point. But that tangent space doesn't come to you with any kind of trivialization unless you've, say, framed your manifold. So in dimension 1, you don't see this issue because I've been talking about oriented manifolds, and in dimension 1, there's not much difference between giving an orientation of a manifold and giving a framing. But if you work in higher dimensions, then you start to see a real difference. And so if you really want to recover field theory from its value on a point, then you should restrict your attention to manifolds which really canonically look locally like R to the n, or in other words, manifolds which have been framed. So issue number one is non-trivial tangent bundles. And to address this, we're going to modify, well, we're going to modify the definition. So let me introduce a little bit of terminology. Let M be less than or equal to D, and let M be a manifold of dimension M. An N frame, or sorry, a D framing of M is a trivialization, I want to say, of the tangent bundle of M. But I want to trivialize this, sort of thinking of everything as being a d-dimensional. So I want to actually stabilize that tangent bundle by adding to it a trivial bundle of rank d minus m, so that this is a vector bundle on M having rank d. So now let me give a vague sketch of a definition. I'm going to define something which I'm going to call cob d, fr for framed, and ext for extended. So this is going to be an example of an n category. Or sorry, a D category. So I'm not going to tell you exactly today what a D category is. I'll say more about it next time. Let me just give you a vague idea by example. So this is an object. So this is a D category. In particular, it has objects. Objects are going to be zero-dimensional manifolds with a D framing. Now, if I give you two zero-dimensional manifolds with a D framing, you can ask about Cobordisms between them, also equipped with a D framing. That is, one manifold is equipped with a D framing whose boundary is the union of the two zero-dimensional manifolds that you're interested in. So morphisms are going to be given by D-framed Cobordisms between D-framed zero manifolds. In particular, these morphisms are themselves D-framed manifolds of dimension 1. And it makes sense to talk about Cobordisms between them, which are going to be the two morphisms in this category cob D-framed. So these are going to be D-framed Cobordisms between D-framed 1 manifolds, and so on and so forth. You're supposed to go all the way down to D. That's what it means to be a D category. And in dimension D, your D morphisms are going to be some kind of D-framed D manifolds which are, there's some kind of Cobordisms between Cobordisms and so on and so forth, so they're D manifolds with corners. And at this level, we'll consider two such to be equivalent to one another, to be the same D morphism if they are diffeomorphic relative to their boundaries. So this is an example of something called a D category. I'll describe all of this more precisely in the next lecture, although still not completely precisely.
So it's just at this last step that you brought up by diffeomorphism?
Yes. And this is an example. It's a D category with a little bit of additional structure. It's a symmetric monoidal D category, or it has a tensor product operation on it. This has a tensor product given by disjoint unions of manifolds. Okay, so what we now want to say, now I want to give you a more precise version of the Cobordism hypothesis. So I'm going to classify topological quantum field theories, but I don't really want to get into the issue of what the right-hand side is going to be in the definition of a topological quantum field theory. I don't want to specify that target D category made out of vector spaces, linear maps, so on and so forth. So what I'm going to do is just let that target category be arbitrary. So let C be another object of the same nature as this object that I described over here, some sort of D category equipped with a tensor product. Any D category with a tensor product, then the following are equivalent. The following pieces of data are equivalent. One, I can study tensor functors from this framed extended category into C. You can think of these as C-valued topological quantum field theories. And two, objects X and C. And the relationship is supposed to be given by setting X equal to the value of Z on point. Now, this is not correct as I've stated it. It's not correct even in the case D is equal to 1, because I told you there were two issues here, and I haven't dealt with the second one. In the case D is equal to 1, we saw that a one-dimensional topological quantum field theory in vector spaces is determined by the vector space that I associate to a point. But that vector space is not arbitrary. It was required to be finite dimensional. So issue number 2 is that not every object can appear as Z of a point. Need to require some kind of finiteness. So I'm going to put finiteness in quotation marks. In the case where the target is the category of vector spaces, there is a good notion of finiteness. It's that we require our vector space to be finite dimensional. In this abstract context, there's an analog of that condition, a generalization of that condition, which you can state in purely categorical terms. It's what I'm going to call fully dualizable objects of C. So, in other words, what I'm telling you is that in this context of D categories with a tensor product, there's some sort of finiteness condition, which I'm calling being fully dualizable. If D is equal to 1 and this is the category of vector spaces, then that's the usual condition of being finite dimensional. But it makes sense in general, and you have this equivalence. Giving a fully dualizable object of your category is equivalent to giving a topological quantum field theory, which is extended and defined on framed manifolds. That's what this Cobordism hypothesis is saying. So let's see how much time I've got. Not very much. So I'm not going to tell you what fully dualizable means today. I'll tell you later on in this lecture series. But let me just sketch where I'm going. So the goal of this lecture series is to explain the statement. Let's label this statement star. Explain statement star in more detail. That is, I want to tell you what it actually means to be a D category. I won't tell you in complete detail, but I'll tell you in much more detail than I've told you so far. I want to describe this particular example of a D category in more detail. The description that I gave over there is a little vague. I'd like to be less vague about it. I'd like to describe what it means to be a fully dualizable object in a D category with a tensor product. And I'd like to sketch, well, that's the first goal. Explain what all of this stuff means. Goal number 2 is to sketch the proof of star. And goal number 3 is to give some examples and sketch some applications. So this is roughly what I want to do in this lecture series. So now let me say what I'm going to do day by day. This might not be completely accurate, but lecture number 1, it just happened. You know what happened in that lecture. Lecture number 2, my intention is to give an overview of higher category theory. I'll say something about what it means to be a D category, how you can think about them, and some of the things that you should bear in mind when working with them. And in particular, I'll give you a more precise construction of Cob D, this extended Cobordism category. So, lecture number 3, I'd like to state the Cobordism hypothesis in more detail. For example, by telling you what it means to be fully dualizable, and state generalizations of it to the case of, say, non-framed manifolds. Like here I gave you a statement, a description of what it means to give a topological quantum field theory, but you were only allowed to evaluate that topological quantum field theory on a very special class of manifolds, manifolds that are equipped with a D-framing. If you want to drop those D-framings, well, there's again a statement like this, but it's a little bit more complicated, and I'm not going to state it right now. I'll state it in lecture 3. And finally, in lecture 4, I think it will depend on how far we get and what the tastes of the audience are, but I can either sketch some proof or give some examples and applications. Depending on what people want to see. All right. I guess I will stop here. Thank you.
Questions? Okay, well, let's thank Jacob again, and we'll resume on Thursday.